Hello everyone. We started discussing about the terminologies used in the electromagnetic system in the last video. Let us continue this in this video also. In the last video, we have seen about the magnetic field, which is nothing but the area around the magnet in which there is a magnetic force. Let's move to the next one. Magnetic flux. It is represented with the symbol B. There is a magnetic force around the magnet which is caused by the magnetic field lines. So, the total number of magnetic field lines around the magnet is called as magnetic flux. It is clearly explained in this figure. See this figure. There is a magnet and around that there is a magnetic field which is represented as beta vector, and A vector represents the area. Angle between beta vector and A vector is represented as theta here. Phi is equal to B into A. Phi is the magnetic flux. It is pronounced as phi, which is magnetic flux, or phi suffix B. P is the magnetic flux density. We will see about the magnetic flux density in the upcoming slides. So phi equal to B vector into A vector, or BA into cos theta. For the phi value or the magnetic flux value to be very high, the cos theta value should be 1, so that it will get the maximum value BA. For cos theta to be 1, theta should be is equal to 0 degree. So, when we put 0 for theta, we are getting the maximum flux. To get the minimum flux value, cos theta should be 0, and hence phi b also will become 0. For the cos theta value to be 0, we have to put 90 degree in the place of theta. The unit of magnetic flux is Weber in SI units, and in fundamental units it is volt seconds, and CGS units it is Maxwell, but familiarly we use Weber for magnetic flux. And what if we have different magnetic flux values for different areas around the magnet? Then we have to sum up all the magnetic flux values for different areas and around the magnet. That is what we have done here. Next is MMF. It is similar to EMF in electric circuits. There, EMF causes the moving of charges in the conductor. But here, MMF, that is the magnetomotive force, causes moving of flux from one point to another point in the core. Or it can also be defined as the cause for producing the flux. See here, there is a bar magnet which is bound with a coil, and through the coil a current is passing. Around the magnet there is a magnetic field due to the current passing through the coil. There are two magnetic poles, north and south poles, that are mentioned here, and the magnetic field follows the direction from north to south. N number of turns of coils are wound around the magnet. So MMF is equal to number of coils wound into the current passing through the magnet. So N into I. Number of turns of coils is equal to N, and the current is I. So it is Ni. From this we can get the unit of MMF, that is, for I it is ampere, for current it is ampere, and number of turns N it is turns. So the unit of MMF is ampere turns. For MMF we have another formula, that is H into L, that is magnetic flux intensity into the length of the coil. We will see in the next slides how we get that formula. Next is magnetic field density, that is represented as B. The total number of magnetic field lines around the magnet is referred as flux, but the total number of magnetic lines under a particular area, that is per unit area, is defined as magnetic flux density. That is what the difference between the magnetic flux and the magnetic flux density. So magnetic flux density B is equal to total magnetic flux lines divided by the area we considered. So total magnetic flux lines is nothing but phi, that is magnetic flux, divided by the area considered is A. So phi by A. See this figure, we have a magnet and this is North Pole and this is South Pole. From the North Pole to the South Pole, the magnetic fields are passing. The magnetic field action is going on. And in that magnetic field, we are assuming our area del A and there is a magnetic flux del Q, del phi in that area. So we get the magnetic flux density as phi by A. And the unit of magnetic flux density can be derived from its formula itself. That is, for phi we know the unit as Weber and for area the unit is meter square. So the unit of magnetic flux density is Weber per meter square. Or we can also have the unit of Tesla. 1 Gauss is equal to 10 power minus 4 Tesla. It is just for the general knowledge. Next is magnetic field intensity, which we see in the MMF equation. That is MMF equal to H into L. And magnetic field intensity is represented as H. It is nothing but MMF per unit length of the magnetic flux path. That is MMF by L. That is what magnetic field intensity is. Or it can also be defined as the strength of the magnetic field. Or else, it is the force experienced by the North Pole when it is placed at a point. Since the formula of magnetic field intensity is MMF per unit length, we can give it as Ni by L. So MMF by length. From this we can get the equation of MMF, that is MMF equal to H into length, that is H into L. That is what we have seen in the MMF slide. And unit of H can be derived from its formula. That is for MMF we know the unit, that is ampere turns, which we got from Ni, divided by length is measured in terms of meter. So magnetic flux density's unit is ampere turns per meter. See this figure. We have a conductor and it is bound with a coil which is fed from current source and a current I is flowing through it. It has a cross section area of A and the total length of this coil is L. N number of turns has been wound through the conductor. So MMF is equal to Ni, we already know it, and H is equal to MMF by length. So Ni by L. Here the length is considered to be L. So it is L, and MMF we already know it, that is Ni by L. Next is the reluctance. It is similar to the resistance we have in electric circuits. Resistance always opposes the flow of current. Similar to that, reluctance opposes the passage of magnetic flux or magnetic flux lines through the conductor. It is equal to the ratio of MMF to magnetic flux, that is MMF by phi. How we get the formula for reluctance? For MMF, we have two formulas, that is Ni or HL. Let us take HL. And phi for magnetic flux, there is a formula B into A, magnetic flux density into area. For B, it is mu H. We will see why we use mu H in the upcoming slides. So mu H into A. MMF by phi for reluctance. So substitute its equations in this equation. So HL by mu H into A. H and H will be getting cancelled. So L by mu A. Mu is equal to mu naught into mu R. So the reluctance S, which is represented with the letter S is equal to L by mu naught mu R into A. Unit of reluctance is derived from its formula itself, that is mmf by magnetic flux. For mmf it is ampere turns and for magnetic flux it is Weber. So ampere turns per Weber. It is shown in the figure. There is a core shown here and the coil is wound in it and it is given AC supply. This coil produces mmf and the magnetic circuit produces the flux. But the core opposing the magnetic flux. That is what is shown in the figure. Next is relation between B and H. Before seeing this slide, I will just explain you what we have seen so far because it is a little bit confusing. So many definitions are there. And magnetic flux is the total number of magnetic field lines around the magnet, and mmf is the cause for producing the flux, and magnetic flux density is the total number of magnetic field lines divided by the area, that is magnetic field lines per unit area, and magnetic field intensity is mmf per unit area, and reluctance is a property of opposing the passage of magnetic flux lines. And let's see the relation between B and H. We already know that B is equal to mu into H, and mu is equal to mu R into mu naught, and mu R is the relative permeability which will be varying according to the medium, and mu naught is the permeability of free space. It is a constant one, that is 4 pi into 10 power minus 7 Henry per meter. Henry is the unit of inductance. Instead of pi, if we substitute 22 by 7 or 3.14, we will be getting it as 12.57 into 10 to the power of minus 7 Henry per meter. Permeability is nothing but, it means says its definition, that is its ability to permeate the magnetic lines through the material. The ability of permeating the magnetic flux or the magnetic field lines through the material is called permeability. For air, mu R is equal to 1. For different medium, it will be carrying different values, and for air, it is equal to 1. It is to be generally known for solving some problems. And see this derivation, and let's see how we get the relationship between phi and reluctance. We already know that B equal to phi by A. From that we can get phi is equal to B into A. And B equal to mu H, we saw it in the last slide also. So instead of B, we can substitute mu H in this place. So we get phi is equal to mu H into A. H is equal to Ni by L in terms of mmf. Let's rearrange it. Ni into mu A by L. See here, we already know the formula of reluctance. It is L by mu A. But here it has been given the reciprocal of it. So L by mu A. So we can give it as 1 by reluctance, and Ni is nothing but the mmf. So mmf by reluctance. Mmf is mentioned with this symbol and divided by reluctance is represented as S. So phi magnetic flux is equal to mmf by reluctance. This is how we get the relationship between the both. We will see the remaining in the next video. Keep watching the other videos also in our channel. Thank you.